new way to do something that was particularly difficult for a long time. So this is, I want to point out right away, this is joint work with Kirill Lazebnik. And this is sort of an illustration of our interpolation of power mappings technique. So Kirill gave a really wonderful talk on Tuesday where he talked about how we can construct really nice entire functions who are modeled on monomials on very large annuli. And we interpolate between these different degree monomials in very thin annuli. So we had fun pictures like this. So the purpose of my talk is I want to convince you, we don't have enough time to talk about all the details of how to prove a Hausdorff dimension 1 Julia set exists. But what I want to do in this talk is I want to convince you that using pictures like this from our interpolation procedure, we can construct wandering Fatou components who have C1 smooth boundaries. So they're going to be infinitely connected. All of the boundary components are going to be C1, and then they're all going to be approximately circles. I want to convince you that the pictures that you can see using this interpolation technique can give you pictures like this. Once you believe that, then the rest is some interesting details, but it's a lot of technicalities and a lot of details. But I kind of want to thrust straight to the main point here. So I won't be saying everything in full generality. So without further ado, I always like to give a little brief history, especially if someone hasn't attended one of my talks before. So here's kind of like a brief history about what we know and when we learned it about the dimension theory of Julia sets of transcendental entire functions. And our first result goes back to 1975, and it's due to Baker. And Baker proved that the Julia set of transcendental entire function always contains a non-singleton, so some uncountable compact connected set. And it follows immediately that the Hausdorff dimension of a transcendental Julia set of a transcendental entire function is always 1 or larger. Of course, in the plane, the largest it can be is 2. And how Baker proved this is Baker proved this more famous result that there are no unbounded multiply connected Fatou components for transcendental entire functions. This immediately rules out totally disconnected sets. And so you always have to have some non-trivial compact connected set. As far as computing the Hausdorff dimension for known functions, so maybe our most common friends in the transcendental entire world are things like sine and cosine and exponential functions. And there's a paper due to McMullen in 1987. He showed that the sine and exponential family, and these contain really big conjugacy classes of other common transcendental entire functions, they always have Hausdorff dimension 2 Julia sets. And so here's a picture of some rescale of the Julia set of some rescaled exponential right here. And we know that we've seen from other talks, this has this really rich Cantor bouquet structure. And it turns out it always has Hausdorff dimension 2. And then like we said, depending on the situation, sometimes we have positive area. It depends on some various dynamical features. The main takeaway is 2 things. One is that almost any function that you write down of a transcendental entire function, it'll probably have Hausdorff dimension 2. Either that or it'll be really difficult to compute. The other main takeaway is that's going to be it's going to be difficult to construct transcendental entire function whose dimensions get close to this Baker lower bound right here. Now, almost all of the major progress right there is due to the work of series of 4 papers of Gwyneth Stollard. Now, in these series of 4 papers, and I have to apologize, I couldn't find the journal article for this one. It was behind a paywall, so I had to do math science, but I got all the other articles right here. But Gwyneth Stollard constructed examples of transcendental entire functions. They're on our friend, the Eremenko-Lubitsch class, where the singular values are bounded, and a lot is known about the Eremenko-Lubitsch class. And over these 4 papers, Gwyneth proves that we can construct entire functions with Hausdorff dimension taking any value between 1 and 2. It's actually stronger than that. If you give your favorite number between 1 and 2, Gwyneth constructs the function that has Hausdorff dimension exactly that. So I think that's really interesting. And Stollard also shows that the value 1, this Baker lower bound, cannot occur in the Eremenko-Lubitsch class. So if Baker's lower bound occurs, it has to be outside of the Eremenko-Lubitsch class. And this was open for a little while until the work of Chris Bishop around 2012, I think. And he constructed a transcendental entire function with a Hausdorff dimension 1 Julia set. And so the Fatou components of this entire function look something like this. It's like some sort of infinite Swiss cheese or some CD disk with a bunch of holes punched into it. But the Fatou component is in gray here. And all the complementary components, they're all C1. They're all approximately circles. And the key to Bishop's construction right here is this really sort of cleverly constructed infinite product. But if you read the introduction to this paper, he talks about how this was inspired by techniques of quasi-conformal folding. And the techniques of quasi-conformal folding are sort of present in this interpolation procedure that Kirill and I have cooked up. So I've always kind of wanted to see, is this actually true? Can we do this with a quasi-conformal folding technique? And can we sort of push this construction further and do new things with it if we have a more general folding technique that produces functions with unbounded singular sets? So that's a little bit of the history right there. So now what I want to do is I want to remind you of the result, especially in case you weren't at Kyril's talk on Tuesday. It'll be a really rapid review. But like Kyril said really well, our interpolation theorem, or our main theorem that we prove in the interpolation power mappings talk, is you sort of have to just feed, it's a machine that takes inputs and produces entire functions. And you have two sequences of inputs right here. So we have some sequence Rj, which we should think radii. And so that's going to determine where the interpolation procedure takes place. And so that has to just be rapidly growing. And then we have some sequence of powers as well. This specifies the powers of the power mappings that we want to interpolate between. So we define sequences like this. And then we're kind of stuck with these coefficients right here. There's sort of some relic of making all of the computations work out, but they're not particularly enlightening. I don't really have a good intuition for what these are. They're just there to make everything work. But we have these radii for interpolation and powers. So once we feed our theorem this, it produces an entire function f and a quasi-conformal homeomorphism phi such that f composed with phi is equal to this monomial on very large annuli right here. So I'm going to be using pictures like this to try to illustrate the main point on the bottom. But really what's going on is that, okay, near the origin, we have f composed with phi is equal to some initial monomial that we're starting off with. Once we hit R1, our first radii specified, we do our interpolation procedure, which I'll describe next. And then we're able to switch to the next model function. F composed with phi is C2 z to the M2. We get to the R2, we interpolate, and now we go up, we increase in power again. And we keep on playing this game over and over. Now, if we want to do any dynamics, we need some extra facts right here. So often in our applications, we'll be assuming that the powers mj, their inverses are summable. And when we have this, we can apply the Teichmüller-Wittich-Belinsky theorem, as Kyril said, that as z goes to infinity, our quasi-conformal homeomorphism converges to the identity. And oftentimes in practice, you'll want a specific rate. So we'll talk about this later on. But that'll often depend on what the precise inputs are. In the most general setting, you can only obtain this sort of qualitative close to the identity estimate. And then we also have control over the singular values. Our function is going to have a multiply connected Fatou component, so it can't have any asymptotic values. And we show that the only singular values of f are 0. So that just kind of comes from the super attracting fixed point that we glued in here. But more interesting are the critical values associated to the critical points inside of the interpolation regions. One thing I want to mention is that there is some flexibility with this construction. We do take advantage of it, but I don't really want to touch on this too much. So we can design the functions so that in this case right here, we have that f has a super attracting fixed point at the origin. But you can make some modifications and do a little bit of extra interpolation, and you can show that you can tweak this construction to show that f has a repelling fixed point. So f has a repelling fixed point at the origin. In particular, we can force the origin to belong into the Julia sets. I don't want to describe how to do this. Maybe we can talk about it after if you want, but you can always assume that 0 is inside of the Julia set, just sort of by tweaking. You choose, instead of putting a monomial in here, you put a Cantor Julia set, and then you sort of bump off the lower order terms. But like I said, we can turn this into a repelling fixed point if we'd like. So that's the main theorem, and that describes what goes on in these big annuli. And what happens in the interpolation region? Well, just go back to Kyril's example that he talked about. So let's say that we want to go between c1 z squared to c2 z to the fourth. What we did is we attached some antenna to this interpolation annuli. And so we can use our stickman to follow what's going on. So we do some folding. We unzip this line right here. And this means that we unfortunately have cut our stick figure in half. We're going to put them back together though. We want to go to z to the fourth. So we apply the z to the fourth mapping on this circle. And this, we still have our stick figure. He is still cut in half, but at least his top and bottom are aligned now. And then we do some clever sort of crunching map, which puts our stick person back together. And this allows the map to be continuous. Otherwise it would be multiple valued and we wouldn't even have a function to begin with. So this is what the folding procedure looks like. And the main takeaways that I want you to have about the folding procedure is that it's designed to be continuous. Our stick figure gets cut and reattached. And this also introduces zeros. Hello? Someone have a question? All right, I'll keep going then. So this introduces zeros into the map. So where our stick person gets attached in this picture, that's a 0. And so inside the interpolation on these antennae that we draw to sort of picture the folding, picture the interpolation, we do have zeros right here. And we also can see that we have angle doubling near some of these points right here. So this also shows that all of the critical points are basically confined to the interpolation region. So that's a really rapid review of the main theorem that Kirill and I had proved. So unless there's any questions, let's talk about how we can apply this theorem to construct Julia sets with these, nice circular C1 boundary components, or Fatou components with that. So we're going to apply our main theorem with the following inputs. So we need some starting inputs. We just choose the C1 term to be 1 and whatever, we'll choose R1 to be 2. It's convenient for a lot of calculations to let the powers of the mappings be powers of 2. So 2, 4, 6, 8. So we'll let mj be 2 to the j. And then once we have all of these set up, we can construct our rj's inductively. And so we have the following formula. Rj plus 1 is equal to Cj plus 1 times 2Rj to the Mj plus 1. Now, you're probably just looking at this and just like, where on earth did Jack get this formula from? And it actually has a nice dynamical interpolation. So we should remember that away from the interpolation region, and so the interpolation region, it's very thin. We do a very efficient interpolation. This is important. So this means that this blue line, the circle of radius twice Rj, is very far away from the interpolation region. And this means in this case that f composed with phi of z is going to be equal to Cj plus 1 z to the Mj plus 1 near this circle. And so I wrote that right here. And so this means that when z is large enough so that phi, the correction map, is close to the identity, f is very, very close to this monomial to begin with. And so what this means is that this Rj plus 1 is defined to be, so f takes the circle of radius 2Rj and it's going to map it onto Rj plus 1. Because if we feed 2Rj into here, we're going to see that we're going to be equal to Cj plus 1 to Rj to the Mj plus 1. So everything's designed so that you have this interpolation region, you double the radius, and then f is going to map that onto the next radius where the interpolation procedure will occur. So that's sort of the key point that's going on here. All right. So now that we've defined our mapping and we have just sort of one dynamical point right here, we want to think more about, what are the important dynamics of this function. And we have the following very important expanding behavior very far from the origin. So it's very convenient that far from the origin that we tile like the complement of a large disk into these certain annuli, which sort of decompose the complement of a disk into region where it's easier to study the dynamics in each individual piece. So what I have right here is we define these annuli AJ. So RJ, again, the region where we interpolate, it's sort of just some constant modulus annulus which surrounds the interpolation region. So if we go down to our picture here, which is in cylindrical coordinates, so everything has this radial symmetry. This right here represents the annulus AJ. Inside, we have the interpolation region, like so. And then we have AJ plus 1 all the way over here. And that, of course, contains a version of the interpolation region. Now, inside of this annulus AJ, what I want to do is first I'm going to draw, maybe I'll use green this time, again, in dashes, the circle of radius 2Rj. We know that this circle gets mapped roughly onto something that's close to a circle, which gets mapped to, it has some radius Rj plus 1. This annulus Vj defined right here is going to surround the circle of radius 2Rj, like so. Now, if we imagine that f was just a monomial, then the image of this round annulus would be another round annulus. And because the powers, if we choose j really large, so that phi is close to the identity, the powers are going to be massive. So that means that this annulus is going to be expanded in a really large way. Now, since F is really close to a power mapping on the screen annulus, we can show with just a simple calculation, but we can kind of just see it that it's because it's close to monomial, that this inner boundary of Vj, well, that's going to map onto some Jordan curve, which is going to be sort of to the left in this picture. So it's going to be contained in the disk of radius 1/4 Rj plus 1. And then this outermost boundary component is going to be mapped by F onto some Jordan curve, so that the disk determined by this Jordan curve contains the entire annulus Aj plus 1. And all of the zeros and all the critical points, they're forced to be in the interpolation region right here. So that means what's going to end up happening is that this Vj, that its image under F is going to swallow the entire annulus Aj plus 1. So we have this important feature right here. Again, it's sort of nice because we know that F is really close to monomial here, and we can prove that it's close to monomial. You can just do a simple calculation to show that you have this very basic dynamical feature. The small thin annulus sort of covers the next annulus where the interpolation occurs. Now, this might be a very simple fact, but it actually has some, if you really push this far, it has some impressive consequences. So what I want to do is I want to go again back to this drawing everything on the cylinder because it's all radially symmetric. But I want to see what happens if we start looking at the zeros of this function and we look at the preimages of the zeros as well. So right here, this is for j large, we have the circle of radius rj. And so I can draw something that's going to represent aj, which surrounds it. And then over here, so what I can do is I can draw the corresponding annulus Vj. Now we know, I actually want to delete those little marks right there. Now, so that's the annulus, that's Vj in green right there. So we know that when we apply F to Vj, it's going to cover the next annulus Aj plus 1. And it's going to do so like a nice covering map. So this is F of Vj plus 1 right here. When we consider the inverse, now what we can do is we can look at a small annulus which contains the interpolation region at Rj plus 1. That's going to contain several zeros of our function. And like I said, we can design the zeros to be repelling fixed points. So it's going to contain points in the Julia set. So what this means is that the preimage of these points in blue right here, they're going to have preimages inside of this green annulus. So I'm going to draw them right there. We're going to have many preimages of these zeros in the second annulus in blue. All right. Well, because f of Vj contains Aj plus 1, well, I can draw Vj plus 1 in red right here. And I know that if I apply F one more time, that's going to map onto something that covers Aj plus 2. And again, the same game that we're playing, that's going to contain zeros of the function contained in the annulus Aj plus 2. So I can consider their preimage, which sits inside of Vj plus 1. And then I can consider their preimages, which sits inside of Vj. So that means the preimage of this red annulus right here, it's going to be some much smaller annulus. And all of the preimages of these zeros, they're going to be very close to each other, like so. And so we can imagine playing this game again. If you went further, I'm out of screen space to do this, but you're going to have another sort of layer of things that eventually get mapped, points that eventually get mapped to 0. So these points in this layer get mapped to 0 after one iterate. These points on this sort of line right here, they're going to map to these zeros and then map to 0. So they'll map to 0 after 2 iterates. This row maps to 0 after 3 iterates, and so on. And everything is going to be trapped inside of this Vj annulus because it expands. And so this means that all of these zeros are going to accumulate. All of the zeros are sort of going to accumulate on some sort of, they're going to detect the outermost boundary of the multiply connected Fatou component that they're in. And they're going to accumulate on something that is close to a circle. Now we can actually say a little bit more. in our situation, if we look at a small neighborhood, so let's use the color blue here. If we look at a small neighborhood of a 0 inside of AJ, we actually have very large expansion. This is a calculation you can do because our interpolation procedure is explicit. But a ball around a 0 of the function, which is on one of these antennae, it's going to be of radius approximately rj. It's going to get mapped onto something which has much larger radius, rj to the mj minus 1. So that means a small ball around the 0 is going to be mapped onto some ball containing the origin, which is going to be stuck between AJ and AJ plus 1. The main takeaway that we have here is that we see that these points in the Julia set are accumulating to some boundary curve in the Julia set, and we're going to see another picture of this boundary curve around a 0 of our function. And so that's enough drawing pictures right now. We can sort of see the structure that we have right here. Now we can go back to the original round picture. So with how we defined everything, the Fatou components, they almost have this exact structure. We have this one layer of complementary holes, which contain a 0 for our function inside. And then there's a second layer of complementary holes, which contain points that are going to be mapped to 0 after 2 iterates. This third layer of holes is going to contain points that are mapped to 0 after 3 iterates, and so on. And they accumulate onto a Jordan curve. And because we have such large expansion of our function, one of these complementary components right here, the dynamics of F are going to act on it by taking this boundary component and mapping it onto this outer boundary curve with small conformal distortion. And because of this fact, if this thing looks approximately like a round circle, the outermost boundary, that means one of these smaller curves is going to look approximately like a circle as well. Because conformal mappings with small conformal distortion, they look approximately like affine mappings. So it's going to be close to an affine rescaling. But again, we can sort of see that we have a picture like this simply after just studying what happens when you look at this, what happens to pre-images of zeros, and with this clever way that we chose the circle of radius 2rj to map onto rj plus 1. Right away, we can sort of see that we have this sort of picture. However, the primary question that we might have is, why does everything have to look necessarily circular? Maybe these zeros can accumulate in a much more exotic way. And I have a little bit more time. So David, how much more time do I have left?
You can go like 6-7 minutes more, don't worry about it.
6 minutes? I can do that perfectly. Thank you.
Okay.
So the point is, how can we show that these things are genuinely close to circles? And how can we prove that they're C1 regular, that they're continuously differentiable? Well, now I want to stop sort of drawing on the cylinder because it's a little bit easier now. Well, it's harder to draw pictures when I have to draw circles. I'm better at drawing lines, but we can sort of see this better when we draw everything in normal coordinates now. So the key point here is that we can strengthen this, given all of our inputs, we can calculate the decay rate. So we can calculate the speed at which the quasi-conformal correction phi tends towards the identity. And it does so at something that's like 2 to the minus square root of j. All that matters for us is this sort of thing is summable. So when a norm of z is approximately rj, we have that phi is close to the identity, and we know, and we have the rate at which as j goes to infinity, that it's going towards the identity. And so what this means is that when we pull back these annuli, so if I go back to these pictures, I was detecting the zeros by pulling back round annuli. And so we can sort of detect, well, what do the round annuli look in this picture? So if this annulus right here is Vj, then in blue, what I'm going to draw is I'm going to draw the inverse image of Aj plus 1, right? F of Vj contains Aj plus 1. So let's look at its inverse image inside of Vj. And so this is going to give me some annulus. Now, if F were genuinely a power mapping, it would be a round annulus. But F is sort of a perturbation of a power mapping. So this annulus, in principle, it could wiggle a little bit. But because phi is close to the identity, and we can quantify how close to the identity it is, we can deduce that the pullback annuli make small angles with respect to each other. And what do I mean by this? If I take the origin right here and I draw a straight line, and I draw a ray through the origin, I can look at the tangent vector that hits this inner boundary component, and I can look at the tangent vector on the inner boundary of the pullback of aj plus 1. It's going to be an analytic curve, so it's going to have a tangent because f pulls things back like a covering map. And so I can look at the tangent here and the tangent here. And the tangents make angle approximately, the difference between the angle of this blue tangent vector and this black tangent vector is going to be of order 2 to the minus root of j. And then if we repeat this reasoning, so if we look at the inverse image of aj plus 2, that's going to be another small annulus inside of here. So it's going to contract even more, because after 2 iterates, this is going to map onto aj plus 2. Then I can look at the difference between the tangent vector, the blue tangent vector, and the yellow tangent vector. And that's going to be even smaller because that's going to be determined by the error at in aj plus 1. So the pullback annuli are making these smaller and smaller angles with each other. And fortunately for us, this gives a total angle deviation of 2 to the minus square root of j plus l as we keep on going forward. And we can make this as small as we would like when j is large enough. So this means that the total angle deviation can only change by a very small amount. So if we draw this sort of boundary curve that we've detected, from this fact that we have in totality very small angle deviation and all these annuli are going to be collapsing onto our Jordan curve, we can deduce that every single point on the limiting Jordan curve has a tangent vector. It's the limit of the tangent vectors in the previous slides along a ray. So we can show that everything has a tangent vector, and because our estimates are uniform, we can show that the tangent vectors change continuously. And because the change is small, everything is approximately circular. So this sort of contracting behavior allows us to deduce these C1 boundary components that are approximately circular. All right, well, that was the main thing I want to talk. So I do kind of want to talk about some sort of open problems related to dimension theory and things that Kirill and I hope that our construction can address. So one thing we want to know is that our Fatou components always have this topology that, they're infinitely connected. We have this infinite Swiss cheese. So one question we can ask, is it possible to construct an entire function that has Hausdorff dimension 1 Julia set, but the Fatou components are not necessarily infinitely connected? And sort of along these lines, so can we have other topology, like what other dynamical features can we change and still have a dimension 1 Julia set? We really only have one example right now, but Kirill and I, we have some ideas on ways to sort of change the dynamical feature to get new examples. So we're working on this, but sort of thinking about, what are necessary dynamical conditions to have dimension 1 or other interesting properties. I think it would be very interesting to see how our construction could explore these sorts of questions. And then the third thing that I want to mention, and then maybe we'll stop, is can the smoothness of the boundary components be improved? It's very weird in dynamics to have something that we really only know is C1 smooth, especially when you're doing holomorphic dynamics. Typically, like if we look at the theory of Kleinian groups, like if you have a quasi-Fuchsian group, its limit set is either going to have dimension bigger than 1, or it's going to be analytic or a circle. And sort of living in the C1 is very uncomfortable for this reason. So I'm curious to know, are there ways that we can improve the smoothness of the boundary components? Because we use this geometric tangent argument, we would sort of need to change the way we argue or come up with other geometric conditions which can allow us to deduce higher regularity of the boundary. All right. Well, you're all a very good audience, so thank you very much. This is a picture from 2019 when we were last all together, and I think I'm right here. I think Kirill's over here, and I see so many familiar friends, so I'm looking forward to when we can all spend time with each other again.
Thank you, Jack, for this fantastic talk.